everybody. I'll turn off my video now, just so you know I'm actually here in person rather than the recording. But I'll turn that off just so it keeps the sound volume a bit better. So you bear with me. I'll go to a blank screen and we'll get to the slides. Okay, so I'll jump into this fairly quickly because I'm sure you picked waterlogging as a topic because you actually experience waterlogging and some of the challenges that faces. So I'm not going to spend a lot of time from a definition point of view, except to say that obviously waterlogging is when the soil's saturated. And so it's typically those air spaces that naturally occur in a soil and that are critical in a soil plants to function effectively get filled up by excessive soil water. And so that's what, you know, by definition is what waterlogging is about. What I want to focus on though in this talk, based on some feedback that Lisa and Michelle gave me, were three things. One was to talk a little bit about what influences the chances of getting waterlogging, because there are a whole range of different factors that contribute to the risk or the chances of having waterlogging occurring. I've also dug around and found some local numbers that we can start to get a perspective on, because I always think it's better if you can relate it to your local patch and an understanding of some of the numbers when you're trying to make sense of this sort of stuff. And then finish off with just what we might be able to do about it and some of the trials that I'm familiar with and some of the work from the dairy industry about what's actually been done in that space. So that's sort of a bit of an outline of what I want to cover in the next 45 minutes or so. Alrighty, so let's get into it. There's 5 things I want to touch on, almost like a bit of theory, before we pull all this together to think about what are the chances of waterlogging occurring. This first one, I think most people will probably be fairly familiar with, so I'll go through it quickly, but just understanding where water is actually held in the soil. And so if we think about a soil, a block of soil or a column of soil, at one end of it is saturated, where every bit of airspace in that soil is filled up with water, and at the other end of that spectrum is where there is absolutely no moisture in the soil at all. That is, it's dried out as if you'd put it in an oven over a period of time. Rarely do soils get right to the bottom of that dry period, but that dried level, but over periods of extended drought, they can certainly dry towards that no moisture level. What we're probably more familiar with is these terms: field capacity or drained upper limit, which is another term for it, and wilting point or drained lower limit. And that's when we talk about the bucket size, we're really talking about that space in between field capacity and wilting point. Reason why I wanted to put this up is just we need to understand different ways moisture is extracted out of that soil. So when we go from a saturated soil or a fully waterlogged soil down to field capacity, it's gravity that causes that drainage or that use or using up of that water. Okay, so it's not a lot to do with the plant transpiration, it's to do with gravity. Plants extract water through that space between that field capacity and that wilting point. So that's when the plants, and I'll talk a little bit more about this a little bit later on, in a sense, extract water out of the soil through the roots, up through the stems, onto the leaves, and then out back into the atmosphere. So the second bit of drainage that occurs in a soil is extracted by the plants. And that's when we talk about this plant available water. So it's the water that the plants use to grow. And the last bit of drainage that occurs in a soil profile is through evaporating by those soils below wilting point. So the plants can't extract moisture, but the soil can actually dry down below wilting point. And that often when we have drought.
Just one moment there, Cam. We just got a couple of, it's not real loud, so if you'd like to move your mic up so we can just hear you a bit better.
Okay, I can't actually get it much closer. Is that any better?
That's better.
Okay, I've tilted my headphones a bit. So, okay, apologies for that, and I'll talk a little bit louder. So yeah, so this last one was the evaporation bit of it. And an analogy I use is, if you could imagine you've been washing a sponge in the sink. When you first pull that sponge out, the water that drains when you hold it up is the one from that waterlogged state down to field capacity. So that's where gravity is draining that water out. If you squeeze that sponge and you start wringing the water out of it, that's equivalent to the extraction by the plants. If you then leave that sponge on the kitchen bench for a few days and it dries and goes hard, that's going from wilting point to that dry area in the soil where you get that evaporation. And I'll come back to the reason why that's important in a tick. So that's the first one I wanted to touch on. So when we're talking about waterlogging, we're really talking about this first bit here between saturation and field capacity. Having said that, obviously the amount of space we've got to store water in the plant available water area, and also then below wilting point, becomes important when you think about what are your chances of getting waterlogged. Because if you've got more space below field capacity, your chances of waterlogging will reduce. Now, I said I was going to put some numbers around some of these soils. There's some great work that's been done by the department just recently in this area, or in the area that I'm showing on here. And I'll show you some results and some numbers on 3 soil types around the sort of Hamilton area. One is for some sodosols, some for some chromosols, and some for some vertisols. So 3 major sort of soil types that we've got around that Hamilton area, because the numbers are different and therefore your chances of waterlogging are going to be different because of that. So just to understand the difference between those 3, chromosols, they've got a strong texture contrast between the topsoil, in this case here about 30 centimetres of topsoil, then going into a heavier clay subsoil. So they tend to be lighter textured on top, heavier textured down the bottom, but the pH tends to be above 5.5, so they're not overly acidic at depth, and they're non-sodic, which is important, because sodicity, which dissolve some of those clay particles so they don't stick together very well, these soils don't have that characteristic. So chromosols, they've got the topsoil and the subsoil that's different, but they don't have sodicity or acidity at depth. Second group I mentioned were those sodosols. They also have a texture contrast between the topsoil and the subsoil. Lighter in the topsoil, heavier clay in the subsoil, but importantly they have sodium levels above about 6, or an imbalance of sodium or calcium to magnesium in the soil at depth, which also causes those particles at times to disperse given the right conditions. So they're 2 different types. And then the third one we'll talk about, which some people may have seen and be familiar if you've come anywhere near the Wimmera, are those cracking clays, or the vertisols, where they have clay the whole way down through the profile. Importantly with these, though, is these soils shrink and swell. So they'll shrink up when they get water in them, and they'll swell up when they get water in them, and then as they dry out, they'll shrink and you get cracks in it. And those cracks allow other bits of material to fall down those cracks, and therefore in a sense turn or self-mulch those soils. So they're the 3 that I'm going to show you some numbers on, which are typical of the soil types around the Hamilton district. So if we think about, first of all, how much water does the soil hold, I'm going to show you some numbers here based on those 3 soil types. So one of them is the chromosols, the second column is the sodosols, and the third one is those vertisols, or those cracking clays. If we start off with the PAW, or the amount of water that's available for plant use, or the bucket size, as sometimes we refer to it, you'll see there's a distinct difference between the vertisols and the chromosols in how big that bucket size is. And that can be pretty significant, because you've got their 60 ml difference in how much water those 2 different soils can hold. Sodosols fitting or falling somewhere in between the 2. The other things to note is that once we get to field capacity and going up to saturation, the size of the pores that we can fill up before we hit fully waterlogged conditions is about twice as high on the chromosols as it is on the vertisols. So you could put 50 ml of water above field capacity, still not be fully saturated in a chromosol where you would be on a vertisol, everything else being the same. And the other thing I suppose just to note is there is a fair bit of water that we can't actually pull out, or the plants can't pull out in your soil profile. So there's quite a bit of water there that's trapped that the plants can't use. But the important one, the take-home message out of this is that the bucket size here changes, and then the amount of storage above field capacity to waterlogging is different on those soils as well. So in other words, some soils are different because they just don't have as much storage space before they get saturated.
Cam, just before you go
Yes.
there, Mark has said that in the Cavendish area, they have a number of curasol soils.
Yep.
And what are their characteristics? They're a bit
Okay.
different, aren't they?
Yes, I could get back to Mark on that. The curasols, basically, they're strongly textured, so subsoil and topsoil, similar to some of the chromosols and the sodasols in that you do have that distinct layering between the two of them. So heavier at the base, less heavy at the top. Didn't include them because there isn't a lot of data on it. There is some, but we don't have the sort of numbers like the hundreds of or 50 or 100 test results that I'm going to show you in a minute. But they're similar in that lighter in the topsoil, heavier in the subsoil type soil profile. So hopefully that covers that one. All right, the third bit of theory that I want to talk on is around water infiltration, which is critical, obviously, if from a waterlogging point of view, what dewaters that soil is gravity or drainage through that soil. How well soils drain is an important component that we need to understand. These things on the left are called disc permeameters, and basically what you do is you go down to a different layer, you sit one of these discs on the surface, and you saturate that soil so it's fully wet, and then in here is a column of water, and you just see how quickly that water infiltrates through that soil when it's saturated. And that's why they're dug in at different depths, because we've got different layers there, so we can understand how quickly water can move through them. So I'm just going to show you some data here that was sourced by Abdul Rub. He's just done this work recently. Lisa, I think, will probably send some people some reports, because some of these soil tests were done on your places, probably people that are on the webinar at the moment. And so I've just combined a whole lot of those together. A bit of a busy slide, this one, but just to explain what's in the table. So we've got our 3 different soil types again. And all I've done is take the top layer. So the surface layer is the top 0 to 20 centimetres. So that lighter textured soil at the top. And I've just got 3 columns here. When you looked at the range of 96 soil tests or soil samples that were taken, or analysis that was done on 96 soil samples, this is the range in infiltration in millimetres per hour. So you'll see if we take the 50% column, or the middle 50% range, in the top soils, the water can get in fairly quickly. 85 mil can be infiltrated through that topsoil within an hour, and as you get to your sodasols and your vertisols, they're much higher. So can absorb, if you like, or allow infiltration of a significant amount of water in an hour. So you can get it into the topsoil fairly quickly. The highest results he was getting are huge up here, but you'll see the lowest 5%. So on some of the soils in each of these soil types, you'll see that the infiltration rate is much lower than what if you like, the average or the middle sort of range is. So they're distinctly lower in how much water can infiltrate. But what's more important is when you then start looking at that contrast with the subsoil. So you go to 20 to 30 down where you've got that layer of heavier clay. And if we start focusing on the 50% one first, you'll see there's a reduction in how much water can infiltrate through the subsoil compared to what can go in the topsoil. So we can get a lot more water in the top centimetres of that soil, but doesn't drain through the subsoil anywhere near as quickly. But the one that we really should pay attention to is this one over here, this lowest 5% of results. If you look at the sotosols and you look at the vertisols, that's 0.01 of a millimetre per hour. So we've got some of these subsoils on sotosols and vertisols that virtually don't let water through. They seal off and don't let water through. So we can get a lot of water, but can't get it to drain out through the subsoil. And so these are the soils that are far more prone to waterlogging. So the key message out of this is that for the sotosols and the vertisols, and to the chromosols to some extent, it's the subsoil that creates the hassle for us, not the topsoil. We can get it in the top, we just can't get it to drain through the soil, but not all sotosols are the same. And so a sotosol like this, waterlogging would be relieved very quickly because that water can drain through into the subsoil, assuming there's no perched water table, but will drain through and therefore move you from that waterlog condition to field capacity relatively quickly. These soils here don't. So it's not just to say if you've got a sotosol you'll be waterlogged, it's only some sotosols that will waterlog, and they are quite different in their rate of infiltration. So really important point to understand, not all soils are the same just because they've got the same soil classification. Two other things very quickly. One is, how do we drain that? So I mentioned what a plant does is it extracts water from that field capacity to permanent wilting point or drain lower limit. That's done through plant transpiration, and that's water being taken out of the soil by the plants. Now, importantly, the way it works, which might sound a bit obvious, but water absorbed by the roots goes up through the stem of the plant and gets evaporated from the leaf surface from these little things on the leaf called stomata. Now, they're too small for you to see, but stomata are little holes. Every plant's got them on the leaves, both top side and underside, depending on which sort of plants you're talking about. And they're a super important thing in photosynthesis. So these little holes in the leaves are critically important to allow carbon dioxide to come in so plants can do photosynthesis. If those little holes aren't open, plants don't photosynthesize. What holds them open is water and moisture. And so when plants become wilty, it's because they lose a lot of water out of those holes. Importantly, those holes are also used to expire oxygen through that photosynthetic process. So they take carbon dioxide in, they take oxygen out of those stomata. A byproduct of allowing carbon dioxide in and oxygen to come out and to hold those stomata open is a loss of water in the plant. So it's not that plants need a lot of water to grow. Plants need a lot of water to hold those little stomatas or those little holes open so carbon dioxide can be exchanged. So plants don't actually use a lot of water, but they use a lot of water to keep the stomata open. So why is that sort of thing important? Because transpiration is a passive process, and the drier the atmosphere, the greater the pull of water through the plant. So we can get in our part of the world through southwest Victoria on a day where the atmosphere is really dry, particularly going into springtime, 6, 7, 8 millimetres of water evaporated off a leaf in a day. We also get the next day, if it was very heavy, cloudy, overcast, and the humidity was very high, that our transpiration or our water loss from those leaves would be very low, down to 0.5 millimetre, 1 millimetre. They can still do similar amounts of photosynthesis in a period of time. So water's not necessarily related to the amount of growth that a plant achieves in a day. Okay, it's just that water is important to keep those stomata open. If the atmosphere is much drier, the more water will be drained or pumped out of the soil or sucked up through the soil rather than on a heavy day. And it's a bit like if you hung washing out, and I know all the fellas know this, you hang the washing out in the morning and it's a really wet, overcast, humid day, come back at night, the washing, there hasn't been this drying process. You have other good drying days where you hang the washing on the line and 2 hours later it's as dry as a chip. Same thing happens with plants. So this idea of plant transpiration is heavily driven by the atmosphere. Why is that important? because if you get a run of high transpiration days, you will drain that soil profile very quickly. If you don't, we can still get photosynthesis, but we're not actually depleting the soil very much of water. And that's what happens typically in winter. We don't get very high transpiration rates because we have a heavy atmosphere. So we're not, in a sense, pulling water out of that soil very quickly at that time of year. And the last one, we talk about a term called evapotranspiration. That includes the loss of water from the soil surface as well as what the plants pull out. It's a combination of the two. And again, the drier the atmosphere compared to how wet the soil is, so that potential soil surface. So, and you'll know if you've ever had mulch on a bit of soil, that stops that surface evaporation, because that connection between the dry atmosphere and the wet soil. I got some work, or Zoe Creelman, who some people may have known, worked for Southern Farming Systems for a period of time, did some probabilities for me, or did some modelling for me to look at the rate of transpiration of plants through different seasons in different parts of southwest Victoria. And here are some of her figures. So if we look typically in the middle of winter, so the 90 days over winter, about half the time the results were coming in at about 230 mil of water we would pull out over that 90 days in winter in a pasture. In a warmer or a more favourable one for plant water use, we'd get up to close to 300 mil. And in a one where the winter was very heavy and sort of very wet all the time, it'd be down to about 150 mil. So in other words, the amount of water we pump out over a winter changes. It changes over spring and it changes over autumn as well. Okay, so it's important to know when we're talking about waterlogging that some years the conditions will be right for waterlogging because we won't be pumping much water out over that winter period. At other times we won't get waterlogging simply because the plants are extracting more water in that eventually wet period when waterlogging could occur. So they're almost pumping at twice the rate as what they would in some other years. So it's a year-to-year thing and even a day-to-day thing, that variation. And you'll see it increases in spring, but not hugely. If we look at the crop side of it, similar sort of figures, similar sort of trend that you get, just the numbers are slightly different around some of those, particularly around the lower decile periods once you get into springtime for some of our winter crops. And the last thing I'll just touch on is that if we start thinking about waterlogging and what's driving the potential or chances of getting waterlogging, is we've also got to realise that we don't always start with a dry soil profile at the start of the autumn break. In other words, we're down at wilting point in those soils when we hit the autumn break. And when Zoe did this modelling, and it was over 55 years, went back and looked at daily rainfall figures and did the modelling on how much moisture would be left in the soil, the plant available water at the start of autumn was on average 76 mil for a pasture and 144 mil for a crop. So that meant you've actually started, your bucket's already partially full before we get going, even getting into the season. And obviously the more water you've got at the start, the less capacity you've got to store extra if we get it during the year. Okay, so hopefully that's covered off on a number of things, because waterlogging is quite simply just about the soil water balance. So if we think about it, you've got a bucket that can hold a certain amount of water. That water has a line which we call this field capacity, and within that you've got this plant available water that we can store. We then have a little bit of extra water that we can store on before it gets to rate the waterlogging above. What fills up that bucket is rainfall. So obviously if we get wetter years or longer ongoing rainfall events without periods of dry in between, we're topping much quicker. What helps empty that bucket is that deep drainage, so that water that can flow through. If we get above that red line, where water rain out the bottom due to gravity, we won't run into those waterlogging problems. So if you've got a soil where, if you like, holes in the bottom of the bucket are quite big and it drains pretty well, what comes in the top will drain out the bottom. If you're on a soil where you don't have holes in the bottom of the bucket, as we saw some of those chromosols and sotosols can have, then you've got potential for water going in to drain out the bottom and just keep filling up the bucket. Other couple of things we've got that extract from that was that plant transpiration I was talking about, but that's highly variable as well, depending on the season that we get. And we've also got soil evaporation, again, depending on the season we've got, but also the amount of cover that's on that soil, whether that speeds up or slows down, how quickly that occurs. And then the last bit we've got is obviously surface runoff. And so surface runoff, really important. If surface runoff's coming from this side of the ledger and running off a paddock onto another one, you're getting rainfall plus surface runoff from somewhere else. But if that soil bucket is full, then that water will run off that soil because it's got nowhere else to go. There is no storage left in the bucket, so it will just overflow and run off the other side. So in a sort of complicated way, they're all the things that are at play about whether a soil is going to get waterlogged or not. And that will obviously depend from almost a daily sort of thing. So the work Zoe did for us, and this is available, and I can give this to Michelle to send around to people. So it's got work of Lake Bolac for crops and pastures, and Hamilton and Cavendish and other places about this balance across that 55-year period of how often do all of those things stack up in certain directions. And just to take one look at one graph out of it, this is the plant available water at Hamilton after a decile 1 year for rainfall, an average year, or a decile 9 year. So in an average year, your bucket by the end of August is virtually full if you've got no plant water to start with. So if you had some plant water there, even in a decile 5 year, you would have a full soil profile. In a decile 9 year, you're going to be saturated and you're going to be pushing into that waterlogging zone, so to speak, past field capacity. It's only in those dry years where you don't actually get to full plant available water. So this has been calculated for a whole lot of sites across southwest Victoria. Now, unfortunately, it's not available for Glenelg Hopkins, as I understand, but in Corangamite a few years ago, we did these, what we call waterlogging susceptibility maps. And those waterlogging susceptibility maps took into account a number of things. They took into account the soil type, they took into account the rainfall and historic rainfall intensity, they took into account topography of that soil, and they took into account things like the potential drainage. And we're able to come up with what was called a susceptibility map. So almost like a risk map. What's the likelihood of these different soils becoming waterlogged at some point in time in those more extreme rainfall years? And you can see there is a difference across the landscape between those. I don't know how difficult it would be to do for the Glenelg Hopkins region, but all the data is certainly there to be able to stitch that together. So there are these susceptibility type maps that bring all those different components together. Okay, I might just pause there for a tick, Michelle. Are there any questions?
Yeah, Steve has put out to everyone, does anyone know where we're at now with respect to our soil water? And the other one from Johnny Gardner is, what were the major differences of soil structure between the highest and lowest subsoil infiltration? So 2 different questions there.
Yeah, okay. I didn't look at your latest soil moisture probe, so I wouldn't know. So maybe someone else in the group can chime in on that one.
I'm just trying to pull up the AgVic soil moisture probe network on my computer while we're talking. So I'll get back to you on that one.
Yeah. Yeah, but it's that really highlights a sort of, you could have your bucket sort of 3/4 full now, but if we get a couple of weeks of reasonable, if you like, drying weather with no rain coming through, then that bucket can go down again and give you more space when you get your next rainfall event.
G'day Cam, Todd Vanning. I'll just butt in. Our moisture probe on June the 3rd was full before the frost, but unfortunately we haven't had an update on it since the frosts.
Okay, thank you.
And Mark Williams has also put up on the chat box, we're at 100% pour on Tuesday.
Yeah, okay. So then what becomes important to how quickly you get to waterlogging is the size of the space between your saturation, which is what the moisture probes are, or you'll have a line on your graph for your moisture probes, and where that full saturation is. If you've only got 40 mil or 50 mil space as opposed to 100 mil, that potentially makes a big difference of whether you strike waterlogging or not. And the other question about soil structure, yeah, the structure would have an influence on that. I'd have to go back, Johnny, and have a look at the exact numbers on that. I only pulled out some average data from Raab's report, but I can certainly go back and have a look at that. But I would suspect that the structure would be poorer. Those pathways would be poorer in the ones that have that lower infiltration rate that you were seeing, whether that's due to sedicity, so you've had dispersion and you've had those individual clay particles block those pathways, or whether it's compacted, whether there's no root growth down there. Any of those things potentially could change those structural conditions that would allow it to drain at depth. All right, I might move on, Michelle. And I'll touch on this pretty quickly because I'm sure everybody has experienced the impact of waterlogging. The reason why it's so important is because for most of the plants that we grow in our part of the world, to take up water, nutrients, so water to run through the plant, nutrients that are absorbed within that water or through diffusion across the root's surface, and to basically grow, plants need oxygen in the soil. There are oxygen. Rice is probably the most common one we grow of commercial crops. And one of the main reasons why we grow rice in water is it makes fantastic weed control because nothing else can cope with being saturated. Rice has a unique feature. It has what they call a snorkel. It's called erenchyma. And it has tubes that run up through the leaves. It sucks oxygen out of the, or air out of the atmosphere and takes it down to the plant roots. So the plant roots can function effectively without needing oxygen around them because it pumps down to them. We do have a couple of plants that are similar to that. I don't know if people can pick that. That's Yorkshire foggrass. Yorkshire foggrass has a capacity to still keep growing in waterlogged conditions because it can create some of these mechanisms to get air down so that it doesn't rely on coming from the soil. Yes.
We're still having occasionally your internet must be dropping in and out. It comes good and then it goes off again. So apologise to everyone. So we got to the fog grass and then you were on to the next one. And then also I've got a couple of questions from people. Do you want to take them now or leave them until a bit later?
I'll take those questions now, Michelle. And on taking them, I'll change my headset. See if that works any better.
Yeah, because you're just dropping in and out of it.
Okay, so what were the questions?
So the question is, so is the best low-cost way to rectify to get the root growth down in the soil?
Oh,
It depends on many different things.
Yeah, the $64 question. Just bear with me. I'll change the, oops. Sorry, people, for this. Where's my...
You are sounding much better.
Am I? Yeah, well, this thing just comes and goes. I don't know why it's doing what it's doing. Okay, well, I might continue on with this one and we'll just see how we go.
Yep.
Yell out, Michelle, if it breaks down and I'll have another crack at another one. Okay.
No problem.
Yeah, so, well, it's a $64 question. How do you improve that subsoil? And I might hang on to that on it at the end because I've got a couple of slides towards the end on around that one. So if that's all right, Michelle, I'll hang off till there. So this other one I've got down the bottom right-hand corner is just some pin rush. It's quite common. We had a paddock at home that was covered in this 30 odd years ago. In fact, all I did was improve the surface drainage on it and nothing else, and there isn't a pin rush on the paddock anymore, because this plant can tolerate those long periods where water just lies on the surface where the paddock's waterlogged. So there are some plants that we have that can tolerate that, but most of the plants we grow can't. And the effect when we've got it is it reduces nutrient uptake, it prunes the roots. So the one on the left there is a soil where a plant where the roots have been pruned because of waterlogging compared to those other ones. So you can imagine the difference that makes for water extraction and nutrient uptake. You get denitrification, which people would be familiar with. So loss of nitrogen there, changes soil biota. So we also get some diseases. So some of the diseases that work under anaerobic or waterlogged condition become more prominent. And importantly, the soil strength declines. So we can get that pugging and compaction. I'll just show you a little bit of work. So Graham Ward did some stuff around the dairy industry in about 2000. And for the basalt soils, for the typical soils that we're on, once the strength of the soil drops below about 4 megapascals for sheep or 0.7 megapascals for dairy cattle, their weight for surface area is greater than what the soil strength will be able to hold the animals up on. And so you'll start to get this pugging because you lose that strength in the soil. So that strength is lost once you get into that waterlogged zone that I referred to earlier. So I want to show you just very quickly a couple of trials. This is one we did at Darren Evans' place at Darrenellum in 2007. It was mainly conducted by Graham Ward and Tim Johnson, so people may remember those names, where we compared with pasture 3 different types of waterlogging management treatments. One was raised beds, so that was the day when raised beds, 2 metre wide raised beds for cropping with a go, and we thought, would it work for pasture? Then we had a control paddock where we didn't do anything, and then we had a humps and hollows. And humps and hollows are about 20 metre wide, where you have a crown on the top and it drains down to these longer sort of drains. And there are different ways you can pull these up. These actually come with a road grader, but there are big rotary drainers that you can use as well. And this was repeated twice across. So we had raised beds on 2 of these areas, and we had controls on 2 and humps and hollows on 2. And just quickly, a few of the results to see what effect that had. And sorry, it was sown to annual ryegrass. And the year that I'll show you the results on it was a decile 8 year. So not an extremely wet year, but certainly an above average rainfall rainfall year that we had. And here are just a couple of the results. So the first one, when I talked about the strength of the soil and how it's lost when those soils get really wet, here were the 3 treatments. So the solid black line is the humps and hollows, and the other 2 that are sort of mixed up together is the undrained one and the raised beds that were pulled up in that typical cropping raised bed fashion. That's about 0.4 of a megapascal. So anything where it dips below that line, sheep will have a major impact as far as the amount of pugging that will occur because the strength of the soil is lost. You can see that we had a period here where it didn't rain for a week or so, things started to dry out a bit, and all of a sudden that surface soil strength increased. But you'll see the whole time the humps and hollows one remained above that, so there would be far less pugging damage that you'd get compared to either of the other 2 treatments for a fairly long period there, from the middle of July to about the end of August. So about a 4 or 6 week period. There's only a small period there where it was below about that 0.4 megapascals from a strength point of view. And I've just put a few other bits and pieces up there. You can also see on there the difference between the amount of runoff that we got off those 3, plus there's some nutrient stuff. But the important 2 I wanted to look at here was the pugging depth. And you'll see the pugging was much less on the humps and hollows because the strength of that soil was better because it didn't have that extra water in it. And not only that, the pasture yield was better on that again. The pasture yield on the raised beds was a combination of the tops of the beds and also the drains as well, which yielded much less obviously than what the tops did. But the humps and hollows tended to be the best one from a pasture yield point of view, and from those other management characteristics that we were trying to get from trying to prevent that waterlogging occurring. Another one, this is a cropping one. We did some work around Werneth, fellas, Troy Misson's place over 4 years, and each year, this is the grazed crop one. We pugged the soil as best we possibly could when it was wet. So we grazed it under the worst possible conditions. So this was typically of what you'd get each year. And you could see the pug marks there from the sheep hooves. This is canola. We just basically grazed it into the ground for 4 years. Every winter, just overgrazed it to see what impact it would actually have on the soil. When we did infiltration on that soil, there was no difference between where we'd grazed and where we hadn't grazed as far as water infiltration goes. And then when we looked at re-sowing the next year, and did it have any impact on establishment over that 4 year period, there was no difference in any of those 4 years to the amount of plants that we got established where it had been grazed and where it hadn't been grazed. So the second message I take out of this one is that soils have if soils have got good biological activity at other times of the year when they're not waterlogged, they will repair themselves, certainly in the topsoil, very quickly. So if we can get the biological turnover and plant growth and activity in those soils seem to have a pretty good capacity to be able to bounce back again if we have pugged them on the topsoil. Subsoil, different story. It's really difficult to get those changes down at that subsoil level, which is really what we need if we'd like to try and encourage that deeper drainage. So just finally, sort of what can we do about it? If we come back to our bucket and we start thinking about this field capacity in that saturated zone, because it's this zone in here that we're thinking about, potentially increasing the plant available water through things like improving our soil structure. So soil organic matter will be a positive towards that, even though it won't be huge. Subsoil amelioration, I think, has probably a chance of making bigger differences compared to that, but obviously there's the cost and the type of technique we use to achieve that. But both of those are looking at increasing that plant available water. So in a sense, increasing this line and also expanding the size of that bucket. Probably can't do much about the rainfall side of it. Will subsoil amelioration or things like subsoil drainage certainly can help from changing this if we've got a really unfriendly infiltration rate at that level, but really difficult to change. Particularly when there's been a bit of talk about, can we get gypsum down at depth and would that make a difference? Gypsum will displace the unfavourable cations we've got, so mainly sodium and magnesium. The challenge you've got though is that needs to have those displaced cations need to have somewhere to go. And we talk about it as a leaching fraction. So unless we can wash them out of the system, they just hang around there, and over time they'll come back again because they haven't been washed or leached out of the system. So being able to leach them out is really important. And so soils that have a very low infiltration because of that imbalance, putting more gypsum down there, unless we can get rid of that stuff, that those displaced cations, it's not going to be a long-term solution to the problem, unfortunately. A couple of other things, through crop and pasture type, we may be able to change that plant transpiration, and we see that quite a bit, certainly over summer. If you leave your green weeds there, you de-water your profile, as sometimes we talk about. But the crop and pasture type can make a bit of a difference on that, particularly length of growing season. Probably can't do much from a soil evaporation point of view, but one I think we can do a little bit on is around this surface runoff. And I've done work at different times in different projects, and I think surface runoff and managing that is something that we can do more with, that we probably haven't really managed very well. Across the whole of southwest Victoria, there are these, there's fabulous contour information. It's called digital elevation models. The catchment management authorities flew them in the early 2000s by aeroplane. They're 1 metre pixel size or 1 metre grid size, and they are deadly accurate of telling you where your water runs. I've used these in a couple of projects and they are remarkably good. What I really like about them is it covers the whole of a landscape. So it's not just a paddock, but you can see from other paddocks where that water's running. And I think these are a fabulous opportunity for us to be able to map and understand where water runs, and potentially help in managing those, either by diverting them in different directions or making sure we capture them and that they don't lie in lower spots on the landscape. And I think if I was looking at a short-term fix to try and address some of our heavier waterlogged areas, this surface drainage would certainly be one that would be worth looking into. And they can be very subtle changes. They don't have to be big, deep drains, but they can be very subtle in helping to understand and manage that water. Lots of notes from Department of Ag, mainly coming out of the dairy industry about other techniques and renovation of wet soils and stuff like that. You can find those on the AgVic website, so they're pretty easy to find. And they've got some good information on that, mainly from a dairy point of view. So just in summary, the likelihood of waterlogging is a combination of your soil type. So that's the plant available water capacity you've got, the space that you've got above field capacity, and how that subsoil drains. So those three play a part in from a soil point of view. Your climate, so your rainfall versus your evapotranspiration, how much goes in, how much goes out, and when that occurs on a daily basis is going to affect your waterlogging. And then your surface topography, or your slope, is going to influence that as well. And then the impact obviously depends on what plants are being grown. As you can see, different plants have different tolerances to that. When your livestock are grazing and what type of livestock, obviously cattle need that higher strength in the soil to avoid pugging or waterlogging, which isn't always the easiest thing to be able to do. And as long as we've got active soil biological activity to repair that topsoil, we can get things back into shape pretty quickly. And then what can we do about it? Obviously avoid grazing machinery at those high risk times. I think, as I said, surface drainage has got a place to play in this that we may not have given enough attention to. And just, long-term working on trying to improve those soil characteristics. But I've come to the conclusion that they're much harder to do than some of the other things like the surface drainage, which I think has probably got a bit more opportunity for us. And on that note, Michelle, I'll call it quits.